Okay, so we're going to start the second half of this lecture by talking about esterification. And esterification is a really important reaction. I can promise you that it's going to come up on the next exam, probably in more than one question. And it always comes up on the final exam and usually in more than one question. It's such an important reaction in organic chemistry. And what esterification is the formation of an ester from a carboxylic acid and an alcohol. So it says here that carboxylic acids react with alcohols to produce esters, and then we also end up with water as a product as well. Okay? Now the acid, there are many different acids that we can use. Oftentimes we just represent H plus like this, like this, a catalytic amount of acid, but you have to have acid to promote this reaction. All right. So it says here, esters, the structure and physical properties. Esters are mildly polar and somewhat water soluble. And if we draw the generic structure of an ester like this, okay, you can see that we have two polar bonds, right, between carbons and oxygens. But here we have R groups, which are nonpolar on both sides, okay? And so that's going to inhibit some of the hydrogen bonding capability just by the size of those R groups, all right? Something that's interesting about esters is that they're found in many foods and that they have very pleasant aromas, okay? So say, for example, if you like the smell of bananas, that comes from the ester known as isoamyl acetate. You like the smell of pineapples, okay? That comes from an ester called ethyl butanoate. If you like the smell of raspberries, that comes from isobutyl formate. If you like the smell of juicy fruit gum, for example, that fruity smell comes from an ester. So again, esters oftentimes have fruity smells like oranges and cherries and like your bananas, pineapples, raspberries. So that's kind of fun. And we actually get a chance to make a few esters in the lab, and we'll get to determine their odors in the lab. So that's kind of interesting. It says here, they boil at approximately the same temperature as carbonyls with comparable molecular weight. Now, what were carbonyls? Does anybody remember what I meant by carbonyls?
Isn't that carbons double bonded to an oxygen?
Yeah, well, what specific type of compounds are called carbonyl compounds? There's two specific types of compounds when we talk about carbonyls. So I'm aware that a carbonyl is a carbon doubly bound to oxygen like this, but when we say carbonyls as a type of compound, it means aldehydes and ketones, okay? So aldehydes, and ketones. So another way of saying this would be esters boil at approximately the same temperature as aldehydes and ketones with comparable molecular weight. All right, there we go. So let's talk about naming esters. It's kind of fun to name an ester. It says here, since esters are formed from the reaction of a carboxylic acid with an alcohol, we reflect that in the naming. Okay, so if we have a generic ester structure down here, the part that comes from the carbon-oxygen single bond, so the single bond, okay, that's derived from the name of an alcohol, okay? And we use that alkyl group as the first part of the name. So say, for example, we had this, okay? Let's say, for example, we had this ester. Well, we've got two carbons over here, so that comes from ethanol. And so we would say ethyl is our alkyl group, right? So we would say this is ethyl something, okay? Now the second step says the base name comes from the part of the acid. So the part that has the carbonyl attached to it, this part comes from the carboxylic acid, okay? And we already learned how to name carboxylic acids. And we replace oic acid with O8. So instead of methanoic acid, we have methanoate, ethanoate, propanoate, butanoate, pentanoate, hexanoate, heptanoate, octanoate, nonanoate, decanoate, so on and so forth. All right, so this molecule that I have in the bottom corner here, this would be ethyl. And since we have 1, 2, 3 carbons, that would be propanoic acid, right? If we had a 3-carbon carboxylic acid, right, like this, that's propanoic acid. We drop ic acid, we drop oic acid, and we add O8. So propanoic acid becomes propanoate. And so this molecule would be ethyl propanoate, like that. Okay, so ethyl propanoate. All right, here are some examples of naming esters. Again, the alkyl portion comes from the part with the single bond, right? This is a single, this is one bond, single. So that is where the alkyl group comes from. We have an ethyl group here, so it's going to be ethyl. And then we have 4 carbons attached to our, or 4 carbons total from our carboxylic acid portion here. So that's 1, 2, 3, 4. So that would be butanoic acid, right? A 4-carbon carboxylic acid would be butanoic acid. We drop oic acid, we drop that, and we change it to O8. So we would get ethyl butanoate. Is shown here. Let's do one more. Remember, this part by the single bond, that's our alkyl. This is a propyl group. So a propyl group. And then our carboxylic acid portion has 1, 2 carbons. So that would be ethanoic acid. We drop oic acid and we replace it with O8. So it becomes propyl ethanoate. Well, with that in mind, let's try some examples here. I'll draw a couple of compounds and you tell me if you can come up with the names. We'll just draw these 2 compounds. I'll give you a few seconds to see if you can come up with some names for these compounds. If you have to look at the rules, of course, do that. If you have an answer for either of them, feel free. All right, I get some names here. Let's take a look at the first one. Here is our alkyl group right here, right? Because this is the single bond. So that is an ethyl. Ethyl. If we look at this part of the molecule here, we have 1, 2 carbons. So that would be ethanoic acid. We drop the oic acid and we end up with ethyl, ethanoate, like that. So good, Johnny, you were right. And in the next one, we have by the carbon oxygen single bond. That's where our alkyl group is. It's an isopropyl group. So isopropyl. And then in the other portion here, we have a total of 1, 2, 3, 4 carbons. So if we have a 4-carbon carboxylic acid, that would be butanoic acid. We drop oic acid and we replace it with O8. And so the name of this compound would be isopropyl butanoate, like that. Give me a thumbs up if you follow me on that. How to name an ester. How to train your dragon. All right, good. All right, I promise I'll ask you some ester nomenclature. Well, now that we've learned how to name esters, you can see that, again, naming esters is a lot like naming the salts of carboxylic acid, right? You start with the part that's next to the single bond first, okay? Whether it's the cation or the alkyl group, you put that first. So sodium, sodium, ethyl, ethyl, and then you look at the number of carbons in the carboxylic acid portion. There's 2, so it'd be FNO8, FNO8. All right, there we go. Now below here, you see some common names. See some common names here. And we're going to look at those common names in a little bit. All right, it says here, preparing esters. Carboxylic acids, again, this is kind of a review. This is where we started at the beginning of the second half of this lecture. It says carboxylic acids react with alcohols to produce esters. Okay, good. The reaction is catalyzed by strong mineral acid and heat is required. When it says a strong mineral acid, it just means something like hydrochloric acid or sulfuric acid. Okay, so we need acid and we need an acid and we need heat. Okay. A molecule of water is released as a product, and this is called a dehydration, right? And you can imagine that dehydration means what? Loss of water. Yeah, it means loss of water, like that. So we take our carboxylic acid plus our alcohol, we heat it up with acid, and we end up forming an ester, and we lose water. Now, where does this water come from? It comes from the hydroxyl from the alcohol and the proton from the carboxylic acid. One of the ways that I remember that water is a product and that heat is necessary in esterification is that what does heat do? Heat causes water to evaporate, and that's why we end up with the loss of water in the reaction. Here's an example of the formation of an ester. If we were to take propanoic acid and treat it with methanol, the propanoic acid has what? 1, 2, 3 carbons. And treat it with methanol. What are we going to lose? We're going to lose water. The water is going to come from this oxygen and this hydrogen, right? And those are all found over here, right here. All right, and what are we going to do? We're going to put the alkyl group in place of the hydrogen. So we end up with methyl, and then we have 3 carbons in our carboxylic acid portion. So propanoic acid becomes propanoate, methyl propanoate. Now, before we move on, we should probably talk about the common nomenclature of esters. Right? Now, if we have a 2-carbon carboxylic acid like this, we call that ethanoic acid. That would be the IUPAC name. And the common name is what? Would be acetic acid. We looked at that this evening. Okay? So if I made an ester of this carboxylic acid, and we already looked at an example, I'll use that same example that we looked at earlier. If we were to have this, the IUPAC name would be ethyl ethanoate. That's the example that we looked at just a few slides ago, and Johnny came up with a name for it. Now, if I want to give you the common name, I use the same principle, okay? But what you do now is you drop ic acid and you change it to ate. So you drop that suffix and you replace it with ate. And so you'd get ethyl acetate, ethyl acetate, like that. So that would be the common name. Let's try another one. Okay, we'll try one more for example here. Let's try this. Okay, we have our isopropyl group and then we have our propyl. And so this would be propyl, isopropyl, propanoate. That would be the IUPAC name. What would the common name be? Well, let's think about it. If I have a 3-carbon carboxylic acid, the common name is propionic acid. So what do? We drop ic acid and we replace it with ate. And so this compound's common name would be isopropyl propionate. All right. I realize that it's tricky. You have ethanoate, acetate, propanoate, propionate. Let's do 4 carbons just to kind of round things out here. Maybe I'll delete this for now. Okay, if we have 4 carbons, right, let's try this. If we had 1, 2, 3, 4 like this, okay, this compound, the IUPAC name would be methyl butanoate. What would the common name be? It would be methyl butyrate. Right? Why would that be? Because when we have a 4-carbon carboxylic acid, right, the common name is butanoic acid, but the IUPAC name is butanoic acid, but the common name is butyric acid. So again, we drop ic acid and we replace it with ate, so we get butyrate. All right, and so that is how you do the common nomenclature of esters. Give me a thumbs up if you follow me on that. Like, I need some time to memorize all these different interesting names, but I can do it. Do anything. All right, good. Good. All right, gonna take some time. Absolutely, it does take time. There's no doubt about it. There's nobody that learns nomenclature of carboxylic acids and esters in 10 minutes. Impossible. Very difficult, I'll say. Okay. All right, let's get looking at a different reaction here. Actually, 2 reactions, and these are really important reactions. I know we're getting late in the lecture here, but I want you to really try to bear with me here because we're going to look at 2 ways to hydrolyze esters, right? This here, the main reaction of esters is hydrolysis, or the reaction with water. The reaction is called a hydration because what we're going to do is we're going to break the ester apart by treating it with water. However, if you just put an ester in water, it's not going to break apart. It's not just going to spontaneously like poof break apart. You've got to have something in there with it, okay? You've got to either have an acid or a base. And what's interesting is that the hydrolysis of an ester in acid or base have different names. Are you ready for this? You're going to love it. The hydrolysis of an ester in acid is called, you ready for this? It's called acid hydrolysis of an ester. Ooh, very descriptive, right? The base hydrolysis of an ester has a sassy name that you've got to know. It's called saponification. Okay? So again, to reiterate, when we bust apart, or smash, or break apart, or hydrolyze, whatever you want to call it, an ester in acid, we just call it acid hydrolysis of an ester. But when we do it in base, it's got this cool name, which is called saponification. If you're wondering where that name comes from, it comes from the fact that pioneers used to take animal fats and they would treat them with lye, which is, I think, a mixture of sodium hydroxide and potassium hydroxide that they would isolate from rainwater that they strained through wood ashes, and they would take that lye and they would hydrolyze the animal fat to make soap. And so saponification comes from, soap making. Okay. All right. There we go. So let's go on from there. Here's the acid hydrolysis of an ester. You take an ester, you put it in water, and you heat it up with some acid. And you're going to blow apart the carboxylic acid, right? You're going to remove, you're going to blow apart the ester. Now, what it's important for you to know is that there are 2 carbon-oxygen bonds, right, in your ester. There's the carbon-oxygen double bond, and there's a carbon-oxygen single bond. I'm going to ask my students who are listening, which one of these bonds do you think is weaker, the single bond or the double bond? And it's not a trick question. Absolutely. All of you are making the correct inference. Yeah, a single bond is going to be significantly weaker than a double bond. And so the bond that you're going to break during an esterification is this bond right here. Okay, so if you were to break that, what you'd end up with would be R, C double bond O, and then you'd end up with OR, like that. Okay, so how are we going to round this out? Well, we're doing the reaction in H2O. We're going to end up with a carboxylic acid and an alcohol. So the hydroxyl comes from the water, and the hydrogen here comes from water as well. And so we end up with a carboxylic acid and an alcohol, like that. Okay, so that's what acid hydrolysis is. Now, it's important to notice that you're doing the reaction in acid, right? This is an acid catalyst, and you're ending up with an acid. When you do a reaction in an acid, you're going to end up with an acid. When you do a reaction in base, you're not going to end up with an acid. You're going to end up with a base. And we're going to talk about that more in a second. But first, I want to show you this example here. This would be a perfect example that I could ask you on an exam. I could say, okay, if you hydrolyze propyl propanoate, hydrolyze that ester in water, but in acid, what are the products going to be? All right, and you would say, okay, I'll draw propyl propanoate, and I'm going to break this bond here. I'm going to put a hydroxyl on this portion, and I'm going to put a hydrogen on this portion. And then I'm just going to look at them, and I'm going to say, okay, I got a 1, 2, 3 carbon carboxylic acid. That's propanoic acid. That's the IUPAC name. The common name is propionic acid. And for my alcohol, I have 3 carbons, so that's propanol, 1 propanol. There we go. Give me a thumbs up if you follow me on this reaction. Acid hydrolysis of an ester. Remember, you're going to break the weaker of the 2 bonds. You're going to break the carbon-oxygen single bond. All right, well, let's talk about the basic hydrolysis or the base hydrolysis of an ester. And again, we call that saponification or soap making. But this time, we don't end up with a carboxylic acid and an alcohol. We end up with an acid and an acid salt. You remember those carboxylates that we looked at earlier? Okay, salt like this. Okay, and again, we'll just leave it like that. We'll just leave it as a carboxylate. You could have any cation. It could be sodium or it could be potassium, whatever. Anyhow, this in itself is a base. Okay, you're like, well, that looks like part of a carboxylic acid, but it's not. It's what's left over when the carboxylic acid loses a proton. This is called a conjugate base. This is the conjugate base of a carboxylic acid. Okay, and that's something that you should have learned in chemistry 101 is acids, bases, conjugate acid, and conjugate bases. And so since you're doing this reaction in base, hydroxide is a base, you're going to end up with a base. Okay, you're going to end up with that carboxylate salt or that carboxylic acid anion. Now, I'm just going to address something here. It's kind of, if you find any of this confusing, I think the most confusing thing on this slide, and I teach this for a living, is that here they say it's an acid salt. Oops, didn't mean to delete that. Here they say you end up with an acid salt, but then they show you as a product a carboxylic acid anion. Let me address why they do that, why they jumble things around like this sometimes in organic chemistry. It's because the cation of the salt is called a spectator ion. And if you don't remember what a spectator ion is, a spectator ion doesn't participate in the reaction. Basically, isn't involved in the reaction. It's there. It has to be there, but it doesn't get involved in the reaction. So let me show you what they mean, or what I mean by that. Here they say a carboxylic acid salt. So let's imagine we have a sodium salt, the sodium carboxylate. Okay, good. So here where they say hydroxide, the hydroxide, it could be lithium hydroxide, it could be potassium hydroxide, it could be sodium hydroxide. Those are the most commonly used bases. So that means that your cation could be lithium. If it was lithium hydroxide, you'd end up with the lithium salt. Okay? If you used sodium, if you had sodium hydroxide, maybe I should delete my lithium, you'd end up with the sodium salt, like that. Okay? If you used potassium hydroxide, okay, if you used KOH, you'd end up with the potassium salt. Okay, so the reason they say here carboxylic acid anion, I think, is that she's trying to make clear that you end up with a base in the end. Okay, you do the reaction in base, you end up with a base. All right, and she just decided to leave out the cation because it's a spectator ion. Now remember, this is just rehashing of what I just told you, but I want to remind you again, an acid can't exist in basic conditions. So the product is the salt of a carboxylic acid using the cation of the base, okay, which I just explained that to you, to balance out that negative charge, okay? Because if you look over here in your products or your starting materials, sorry, you have no charge. So since she has a negative charge here, you have to end up with a negative charge there. If she had included a cation, let's say, for example, sodium, if she had said NaOH, she would have to include that over here. But again, she just decided to leave it out. Give me a thumbs up if you follow me on what I'm trying to explain. Just some of the nuances here. Just feel like this slide kind of, she kind of says one thing and then she presents something else. But I get her point. I get what she's trying to do. Okay, so saponification. And here's an example of saponification. If you've ever heard of a triglyceride before, if you like things like ice cream, you like to eat triglyceride. So here's an example of a triglyceride. You guys remember this molecule from the alcohols chapter? Who remembers this molecule right here? If I draw this, 1, 2, 3, trihydroxypropane. Does anybody remember the common name of that molecule, of this alcohol? The common name for it. I had a whole slide about it. Yeah, it's glycerol. Yes, this is glycerol. And so here's glycerol right there. Okay, so if you add an ester to each one of these hydroxyls, you have this, which is a triglyceride. So a triglyceride is basically nothing more than glycerol with 3 esters on it. Okay, now if you hydrolyze that, okay, you end up with glycerol, of course. That's the alcohol, right? Because you're going to break the carbon-oxygen single bond, which is the weaker of the 2 bonds. And you're going to end up with all of these 3 carboxylates, okay, like that. And then the metal is going to be the cation, like that. And that is actually what soap is. So this shows you saponification. If you go on YouTube and you Google, soap making from animal fat, you can almost find Avogadro's number of videos of people doing that. If you have some spare time, check it out. It'll help you remember what the heck is going on in the reaction. All right. Notice also that it says here, M is the metal hydroxide. It says here that it can be sodium or potassium, right? So this could be, right, it could be KOH or it could be NaOH. And if you're wondering, like, when would I use which one? Well, it depends on the situation. It could depend on what you have available. Okay. Anyhow, there you go. That's the soap making process. Here's the simplified action of soap. This is how soap works. You see this thing in the middle here? This thing. A good scientist shouldn't use the word stuff or thing, but it's appropriate right here. This is dirt. Okay. So what you see in here, this is like, maybe this is a ball of earwax or something, but this is dirt or grease or something, right? Something that's non-polar, right? Oils that we have on our skin, those are non-polar. So what happens is when you wash your hands with soap, the structure of the carboxylate in a soap looks like this. So you have, let's say it's a sodium salt, okay? And if you're like, do you mean like Irish Spring or Ivory or Dove or Calgon? Yes, all those soaps. This is the structure of a soap, okay? Nothing more than that. It's just the carboxylate of a fatty acid. So the blue portion, all these little blue spheres here, that's this portion here. And then the squiggly red tail, that's this portion right here. And so what happens is the squiggly tails are nonpolar, right? Because they're just carbon-carbon and carbon-hydrogen bonds. And so that's going to interact with the dirt. And then the carboxylate head is polar, right? So that's going to interact with all the water molecules. Okay? It's a salt. It's going to dissolve in the water. And so what that creates is a sphere that surrounds the dirt particles, and we call that a micelle. Now, these are very small. They're microscopic, but what they do is they enable the dirt to solubilize, or to emulsify in the water, and that's how we end up washing our hands. Okay, if you've ever tried to rinse grease off of your hands in water, it doesn't work, right? If you ever try to clean a frying pan after you clean bacon or cook bacon on it, if you just use hot water, it's not going to get it clean. Just use cold water, it's not going to get it clean. You've got to use soap, which has the capability of cutting the grease, right? It makes these micelles, which are going to end up being emulsified in the water, and then they're going to get washed down the drain. Okay, so that's how soap works. Now you know. Something to get excited about. All right, give me a thumbs up if you follow me on the whole soap concept and how a micelle works. All right, good. Perfect. Okay, great. Thanks, you guys. Good. All right, let's keep going here. And let's talk about polymers just for a quick second here. And the reason why polymers come up in the esters chapter is because there are polymers that contain esters. They're called polyesters. And I'm sure you've all heard of polyesters before. So polyesters are condensation polymers. And if you're like, what's a condensation polymer, Mr. Dion? Well, what was condensation? What is condensation when you're in grade school, right? It's loss of water. And so when we do a bunch of reactions with esters and alcohols where we lose water, we can form polymers. It says here they're formed by eliminating a small molecule like water when combining a diacid and a diol. So what's an example of a diacid? I don't know. We could choose, remember, Oh My Stars Go Away? Who could name this diacid? One with 2 carbons in it. Anybody give me the name of this one? A 2-carbon diacid. We looked at it this evening. Oh, so it's Oh My Stars, right? Oh My Stars Go Away. So it's oxalic. Okay, so 2 carbons is oxalic acid. Okay, so if we were to take a diacid and react it with a diol, like ethylene glycol, okay, which is antifreeze, we could make a polyester. Anyhow, let's take a look at an example of that, which is shown here in the synthesis of this interesting polymer, this interesting polyester called polyethylene terephthalate. So we have our ethylene glycol, the IUPAC name is 1,2-ethane diol, and we have this molecule here, which is a diacid called terephthalic acid. So if we were to do an esterification reaction, right, we're going to end up losing H2O, and then we're going to form an ester between these two. Now what have we got? We've got an alcohol over here, and we've got a carboxyl group over here. So we can just keep doing esterification after esterification after esterification, and we end up with a polyester, right? There's an ester here, ester here, ester here, ester here, like that. And again, it's called a condensation polymer because every time you form a new ester bond, you lose a molecule of water. And polyethylene terephthalate is found in all kinds of things like mylar, plastic bottles, garbage bags, CD cases, polyester fabrics, so on and so forth.